All right, here we go. This is chapter 11, problem set number 1. First one we have here is question number 3. Question number 3 says, what happens to the initially stationary yo-yo if you pull it with a string, A, force F2, and then B says force F1, and I bet C is force F3. So when we approach this problem, I think what we have to consider is there's two things going on here. There's the torque applied by the string, and then there's also a force by the friction here. So if we just get a sense of, well, I mean, I can draw it on here. So there's a frictional force right here with the ground. So there's always going to be a frictional force, because without the frictional force, it couldn't turn. But we're going to use this point of contact right here as our pivot point. And so all of our R vectors are going to be drawn from that point. So if we look at, for example, we'll do them in order. We'll do F1, F2, and F3, even though that's not what the problem says. So if this is F1 right here, there's a point of contact. Now, it's a yo-yo, so the string is wrapped around the center peg right here. Wrong color. So when I go to do my R vector, there's my R vector. And then I'll go to do my string vector. We're going to call that F, they call it F1 right there. Well, what you're going to notice is those are perpendicular, which gives you the maximum here. And then you have to apply the right-hand rule. So you're going to point your fingers in the R direction and then curl your fingers in the F1 direction. And when you do that, can't see me doing it, but I'm doing it, you're going to notice that your thumb points into the page. And your fingers are curling in the clockwise direction, so your thumb is into the page, and the yo-yo should spin this direction, which is weird. Let's do the second one and see what happens. Oh gosh, what the heck was that? Much better. So this time we have F2 here. Actually, this is F3. And then where's our R vector this time? So again, we're still using this pivot point here. So this time, if we point our fingers in the direction of R and curl them toward F3, we're going to notice that the thumb points out of the page. Therefore, it's going to rotate this way because that's the way you curl your fingers. So each of these is, basically we're going to try to find the torque. The torque is in R cross F. R vector cross F vector. And if you're going to do this, you have to use the right-hand rule to figure out which way, and the thumb gives you that direction. So what about this last one then? Well, in the last one, you're pulling but what do you notice about, so here's your R vector, here's your F vector, and you're going to notice they're in the same direction. One of the consequences of R cross F is R cross F, which you need R, F that are perpendicular to one another. And you can notice those two are parallel to each other. So this one, torque is equal to 0, and it won't spin at all. In fact, if you do that, and it's resting on a table, it would just slide along the table this direction with some speed dragging it across the table. All right, let's look at question 7. A rhinoceros beetle rides the rim of a horizontal disc rotating counterclockwise like a merry-go-round. All right, if the beetle then walks along the rim in the direction of the rotation, will the magnitudes of the following quantities increase, decrease, or remain the same? Okay, so let's give a little, get a sense of this here. So, okay, so let's say this is our rotating disc. Now, it says it's rotating counterclockwise. So this would be, that's like a clock. So this, okay, so it's rotating this direction. Okay, no problem. Now, we got a beetle. I want to draw a beetle. Okay. So we want to know what's happening here. Now the whole thing is rotating, and the beetle is rotating on it. So what would happen if the beetle walks along the rim in the direction of the rotation? Okay, what will happen here? So the beetle is going to walk in this direction. Now, if you remember what happens when you walk, right, you actually have to push back against something in order to walk. But here's the thing that I think they're trying to get at, is that this is a closed system. And in a closed system, momentum is conserved. So if the beetle walks in the direction, he's speeding up in this direction, what has to happen to the actual disc itself, right? I think it has to slow down to compensate, but the total angular momentum is conserved. That's the total angular momentum. So it says if he walks in the direction of motion, the angular momentum, so the angular momentum of the disc beetle system stays the same. The angular momentum of the beetle increases because he's going faster in that direction, which means that the angular momentum of the disc has to decrease because it actually had to slow down in that direction. So, but if the amount that this one increases and the amount that this one decreases are exactly the same because the total has to stay the same, which is really cool. The next part of the question says, well, what would happen if he walked the other way? So if we take our beetle, and instead of walking this way, what if we started walking this way? Since he's already moving with the disc, if he started walking this way, he'd actually slow down relative to the disc, but he's actually pushing the disc in the direction it's already going, which means the disc would actually speed up. So the angular momentum of the disc beetle system, again, stays the same because it's a closed system. There's no external torques, but the angular momentum of the beetle would decrease and the angular momentum of the disc would increase. As long as your system is closed and there's no outside torques, your angular momentum is conserved. All right, question 9. Question 9 says, you have this graph here. It gives the angular momentum, L, of a wheel versus time. Rank the 4-lettered intervals according to the magnitude of the torque acting on the wheel, greatest first. So this one's pretty challenging, and to really understand it, we're going to have to think about the linear analog for this. So what does this look like in a linear graph? So I have up here angular momentum, which is L, is angular momentum and time. So what would this look like if this were, instead of angular momentum, what if this was linear momentum and time? So we have time here, we have a linear momentum up here, and let's say I had some line, whatever it was, it doesn't actually matter. Let's say it looks like this. So is the slope of this line something important? Well, there's a couple ways we can approach this. So if I look at 2 points on this line, for example, how would we calculate the slope of this? Well, this up and down would be the change in the momentum, and this left and right would be the change in the time. So we call the slope the change in the momentum divided by the change in time. And let's see if that makes any sense. Now, what do we know about the force? So in general, force, we'll call the unbalanced force. The force is equal to mass times acceleration. But what do we know about mass and acceleration? Well, the acceleration is actually the change in velocity divided by the change in time. What's mass times velocity? Isn't that momentum? So wouldn't this actually be equal to the change in momentum divided by the change in time? So this force that we were talking about earlier, one of the ways we can conceptualize force is force causes a change in momentum that happens over some time. But look at this here. I have this idea repeated twice. So if I have a momentum time graph, the force is the slope. I think we're going to do a little analog work up here because we're going to see a similar situation where if force is equal to ma, then doesn't that mean that torque is equal to I alpha? And working off the same logic here, that means this is equal to I delta omega delta t. But what do I know about I and omega? If you combine I and omega together, this is going to be the change in the angular momentum divided by the change in the time. And so this torque we were referring to earlier is the change in momentum divided by the change in time. I could get that here by looking at the slope of any segment. Therefore, the torque is equal to the slope. So if you have a angular momentum time graph, the torque is the slope. So now the question says, in this figure gives the angular momentum magnitude L of a wheel versus time. Rank the 4-lettered intervals according to the magnitude of the torque acting on the wheel. So if torque is the slope, the one with the biggest slope has the biggest magnitude. Now one thing that is important here is they're asking for magnitude, so the plus and minuses don't work. Look at A, in section A, slope equals 0 because it's flat. In section C, slope also equals 0 because it's flat. In B, slope I would say is medium. And in section D, I would say the slope is steep. So if I had to rank them, greatest first, I would say D, then B, then C equals A, and these are both 0. All right, question 11. A cannonball and a marble roll smoothly from rest down an incline. Is the cannonball's time to reach the bottom and translational kinetic energy to the bottom more or less or the same as the marbles? All right, so let's work this out a little bit. So let's get an incline here. So we have two things here. We have a bowling ball and a marble. Here's our bowling ball. There's the holes. And we got a little marble. One of the things implicit about this is that the mass and radius of the bowling ball are much bigger than the mass and radius of the marble. So the question is, does it matter? All right. And there's a couple ways to consider this. There's the forces in kinematic way, and then there's the energy way. So I think the energy way is a little bit easier, but let's look at the forces way to start. So if I take my ball and I draw the forces on my ball, I know from the center of mass the Earth is going to pull it down. At the point of contact, two things are happening. There is a normal force running through the center of mass, and there's the frictional force that is along the ramp opposite the direction of the rolling. And so when I look at this, break this up into its components, we know that angle is the same as this angle here. No big deal. And so a couple things happen. This is for a ball. Now it's either for the bowling ball or the marble. It doesn't matter because they're both solid spheres. So I'm going to express my forces and my torques. So let's do the F net in the x direction. We'll call this the xy direction. So F net in the x direction is equal to the mass times the acceleration in the x direction. We have two forces. We have the mg sine theta. That's this component right here. And we have the friction, and the friction is opposite. I use this one minus this one because I know it's accelerating down the ramp, so it makes it all positive. So I have ma is equal to mg sine theta minus the friction. Now, I may need a F net in the y direction coming up here. I'm going to pause on it for a second, and let's see if we can do this with torques. So what do I know about the net torque? Well, the net torque is equal to I alpha, in the same way that net force is equal to ma. If I look at this, I have to decide on a pivot point. And you can either pivot it at the center or you can pivot it at the edge. Either way, it doesn't matter, but you have to be able to use the correct moment of inertia depending on where you're going to pivot it. So I'm going to pivot it at the center so I can use the solid sphere pivoted at the center. Therefore, if I'm using this as my pivot point, the mg can't supply a torque because its radius is 0. The normal force can't supply a torque because its angle is 0. So the friction is the only thing. So the net torque is equal to R cross F. So in this case, it's RF, where F is the friction, because my R vector would be there. So RF. Set these equal to each other. Now, I'm using a solid sphere, So the moment of inertia for a solid sphere is 2/5 mr squared. And I know that the relationship here, linear acceleration is equal to alpha r. And I bring that up because I have a linear acceleration here, but an angular here. So I'm going to make a substitution, bolt these into here. We're going to see what happens. So 2/5 mr squared times a over r is equal to rf. If you're playing along at home, one thing you're going to notice right away is that if I multiply both sides by r, I get r squared on this side and r squared on this side. And they somehow magically disappear. And so I'm left with 2/5 ma is equal to f. So this gives me an expression for the friction. And so now I'm going to come up here and I'm going to insert this into my friction up here. And then I put this expression. So I have negative 2/5 ma on this side, and I have basically 1/5 ma on this side. And so if I add this to both sides, I end up with, so this is, I'm going to add 2/5 to 5/5 over here. And I can see I have one m on each side, so I can divide. And I'm going to also move this fraction over here. So I have a is equal to 5/7 g sine theta. So two really important things happened. One, the radii magically disappeared, and the mass magically disappeared. And so if I go back and I look at this, what I'm going to notice is that if I look at it from a kinematic sense, delta x, v0, v, a, and t, they both have the same delta x, they both have the same initial velocity, they both have the same acceleration, and then therefore they're going to have both have the same time, and they're going to have the same velocity. So all of these quantities are the same for both, which is a crazy idea. The next thing that they want to talk about is the translational kinetic energy. So as the ball rolls down, we know it's picking up rotational kinetic energy and translational kinetic energy. The translational kinetic energy is the one we're familiar with, 1/2 mv squared. And this is 1/2 I omega squared. And what's interesting about this is that we decided that they both have the same speed, right? But when it gets to the bottom, for this guy, he's going to have a huge translational kinetic energy because it's 1/2 big M v squared. But this guy's going to have a much smaller, because they have the same speed, but 1/2 little m v squared. So when it gets to the bottom, the translational kinetic energy is much bigger for the bowling ball than it is for the marble. And that's it.